Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Listeners have asked us to provide pointers to some of the resources we talk about on the show. We now have links to books and articles referenced in recent podcasts that are available on our website. We also offer full transcripts. Go to jimruttshow.com. That's jimruttshow.com.
Hey, loyal listeners, we're trying an experiment here on the Jim Rutt Show. It's a new sub-series called Who Are You? One of the hallmarks of the show has been my pretty extensive preparation for guest appearances. I read their books or their scientific papers or read transcripts of their YouTube videos. Then I cook it down to 6 or 7 pages of topics to discuss. I spend on average 10 hours preparing for each full-length episode. And I select guests based on who I think would be interesting or who might have something interesting to say. In the Who Are You sub-series, we're going to reverse all of that. I'm not going to know who the guest is, what they want to talk about until showtime. And you, the listeners, will pick the guest. Hence the name of the sub-series. My first question will be, who are you? The guest will need to be prepared to start from ground zero, explaining who they are, what they do, and why anyone should care. I'll need to be prepared to adapt on the fly to what I hear, and then to try and steer the conversation in a direction that both the audience and myself will learn something from that guest from what he has to say. My producer, Andrew Blevins, will be asking for nominations for the first Who Are You guest via my Twitter account. That's at Jim_Rutt, and on my Facebook account. Fortunately, I'm on a 9-month break from social media, so I won't see the nominations or the ensuing discussions. Or you can just send your nomination to nominations with an S at jimruttshow.com. That's nominations at jimruttshow.com. Andrew will select the subset of the nominations that he believes are reasonable and will list them on an online poll. A link to the poll will be posted on my social media accounts, and people will be able to vote for their favorite. After the poll closes, Andrew will contact the nominees in the order of votes that they have gotten. And the first one to say yes will be the guest, and it'll all be unknown to me. This is an experiment, and it may fail, but it ought to be good for a laugh, if nothing else. If it's successful, we may choose to launch it as an ongoing sub-series on the show. So think about who might be a great guest for the show that I'm never likely to encounter, and send their name along to nominations with an S at jimruttshow.com. Thanks.
Today's guest is Terrence Deacon. Terrence is a professor of anthropology and neuroscience at the University of California at Berkeley. Professor Deacon's research has combined human evolutionary biology and neuroscience with the aim of investigating the evolution of human cognition. His work extends from laboratory-based molecular neurobiology, that's a mouthful, to the study of semiotic processes underlying animal and human communications, especially language. His theoretical interests have focused on the problem of explaining emergent phenomena such as characterize such apparently unprecedented transitions as the origin of life, the evolution of language, and the generation of conscious experience by brains. He is the author of The Symbolic Species, The Coevolution of Language and the Brain, and regular listeners will recognize Symbolic Species as one of the books I reference the most. While almost 25 years old, I still believe it is an indispensable work in understanding how language came into being and how humans have so vastly exceeded our very close genetic relatives, the great apes, in manipulating the world and understanding our universe and ourselves. Welcome, Terrence.
Thank you. I appreciate that introduction. You're exactly what I was after.
Yeah, exactly. I think for a long while it annoyed me that people didn't know that book. I've been telling people about it now for at least the last 20 years, and hopefully I've spread the word at least a little bit, because I do hear it referenced more than it used to be.
Yes, I think you're right. I thank you very much.
I'm sure I'm not the only guy, right? Today we're going to talk about Terrence's 2011 book, Incomplete Nature, How Mind Emerged from Matter. And it's going to be a lot of fun doing this episode because we're going to bring together many themes we talk about here on the Jim Rutt Show from previous guests. We're going to talk about emergence, David Krakauer, Matt Perkowski, we had on recently, Jessica Flack, some others. We're going to talk about consciousness, as we have talked with Antonio Damasio, Christoph Koch, Bernard Bars, Embry Brown, Ian McGilchrist, and a whole bunch of others. We're going to talk about complexity. We're going to talk about open-ended search. And one of my favorite, actually good friend and long ago guest, Stuart Kaufman, is going to figure fairly substantially in the tale here today. So this is really going to be quite fun. The book covers a lot of ground, and it's a careful and deeply constructed argument. And in the time available, I'm not going to be able to do total justice to the book. So if you find this interesting, get the book. Let me warn you, the book is not an easy read, but it is accessible to the non-specialist, so long as you have lots of caffeine and read slowly. I will be picking and choosing high points so that we can move along in our allotted time and leave enough time to the final chapter, which is where Terrence gets into consciousness, which we know is a topic of interest of mine and to our audience. So with that, I'm just going to jump in, if that's okay.
I'm ready.
Are you ready? Well, let's start. Good place to start as any, the beginning. You have a chapter 0 called absence. And this is a key idea, and you talk a little bit about it in general, and then you talk a little bit about the story of zero. So why don't you tell us why absence is such an important part of your argument?
Well, as I say in that chapter, I think it's the one area where we just haven't integrated absence, even though it's implicit in almost everything we do in the sciences. We haven't integrated it into our physical theories, or even into our theories about our mental experience and so on. And by absence, I mean a range of things. The main thing I refer to, and of course the book will be about, largely is about the kind of absence that comes into play when we talk about purposes or meanings or values. And in particular, a classic philosophical term, teleology, about purpose and direction and aims and things like that. But when we think about even the trivialist kind of absence that we use in the words I'm speaking now, the meanings of those words are actually not in the sound, not in the physical attributes in any sense, but the words, the meanings, the ideas are about something that's not present. And I sometimes have used exotic terminology, like to call this a constitutive absence. That is, the constitution of a word is really linked to what it's not. And the point I make in terms of absence is that, in effect, everything about us is with respect to absence. That is, both the possibility that I might not be here if I don't do certain things, that I might disappear, that I come from an absence, and that most things that I'm interested in have to do with something present that is linked to what's present by virtue of what it's not. And that became sort of a driving interest in this, because almost all of the questions that I think are at the core of our greatest problems in the sciences and actually divide the sciences from the humanities are oftentimes things that deal with absences. And I became very fascinated with this and trying to understand why it is that in the sciences, we couldn't really seem to incorporate it into our theories. Why is it that we have a problem with what's absent in our experience? That is, consciousness is always about something, but what it's about is not the stuff of consciousness, whatever that might be. That troubled me, but as I said, it goes to almost everything that's of interest to us. And the reason I called this chapter 0 was not just that it's before the first. It's actually because I think it's the same problem that we had in the West with the very concept of zero. How it is that we mark something that's not there. Interestingly enough, it wasn't until the West finally accepted Arabic numerals and their ability to mark a value for absence, for zero, for nothing. It wasn't possible until we had that to begin to produce this number system which is recursive, in which we count up to 10, and 10 involves a zero. And then we start over again. And each cycle in this recursive number system we have is sort of marked by this mark for where you have to start. You have to start at zero. You have to start before you have a value. What was interesting about zero is it's also a problem that dogged early philosophy. Zeno's paradox is a classic example. This idea that an arrow is shot towards a target, for example, and that in the first part of its flight, it covers half that distance. In the next part of its flight, it covers half the remaining distance, and then half the remaining distance. It would sound like there is an infinite number of half distances to cover, and so that maybe the arrow couldn't finally reach its target. And this is because we really didn't know how to deal with absence. And absence and infinity are, in this sense, related. We recognize this because whenever we divide something by zero, we get an infinite value. And multiplying things by nothing eliminates them. There's this odd effect of working with absence, of working with zero. And I think the way that we resolved Zeno's paradox, which ultimately helped us generate the mathematics that we call calculus today, was learning how to work with infinitely small divisions. And the way we've done that is by recognizing that, in a sense, you can't quite do it by actually counting anything. It's actually a converging effect. We recognize that things get smaller and smaller. And so when there's a velocity, we recognize that a velocity is distance traveled over time. But at any moment in the velocity of an object, at any moment, it's not traveling any distance and it's not taking any time. And yet we know at every instance it has a velocity. That's what we discovered, a way to work with that problem when we developed the calculus. My guess is that our problem with dealing with absences in terms of consciousness, in terms of representation, in terms of end-directed processes, purposive processes that are headed somewhere that it doesn't exist, processes that are developing towards something that is not in existence yet. It's a similar kind of problem. And so I tried to set it up by helping people understand that maybe the problem, even the problem of mind, has to do with our difficulty at dealing with absences.
Very interesting. And you also point out that at least some of the more reductionist versions of our theories of everything essentially imply that we don't exist, or at least the things that we'd actually recognize as ourselves. I'll give an example from my wife and I's personal life. A dear friend of ours recently died at a relatively young age. We decided to do a 10-hour drive and go to her memorial service. Whatever it was, that intent to attend her memorial service essentially produced a lot of motion on a lot of atoms for like a 3-day period. And so this thing, which a reductionist theory of everything, at least, would not even acknowledge existed, caused all kinds of running around in the physical universe, consumption of hydrocarbons, drinking way too much alcohol, etc. So I'm assuming that's the kind of thing you're pointing to that needs to be explained.
Exactly. It's almost everything we do is with respect to something that doesn't yet exist. All of our actions to make things happen, bring things into the world, are really about that absence, that it's not here yet. I actually think that this is the essence of what it means for something to be alive. Because to be alive, of course, is about maintaining your existence. Rocks don't have to maintain their existence. The atoms of my body don't have to maintain their existence. But somehow I have to maintain my existence by doing constant work, because there's something about the universe that makes the kind of thing that I am break down and disappear. And this is one of the real challenges. So we're always living our life with respect to our potential absence, you might say.
Very interesting. Well, I'm going to jump way ahead then, and you open the door. Let's talk a little bit about second law of thermodynamics and how life is at least a local hack that defeats it.
In fact, it's what drove much of the writing of this book, is recognizing two things. Number one, that there's a constant, you might say, unavoidable tendency for regularities in the world to dissipate, to break down, to regular features, constraints, things that hold things back. For example, these tend to break down. This means that order breaks down. When the second law of thermodynamics was discovered, it produced a kind of malaise because it suggested that the world itself, the universe itself, was running down and would eventually come to a halt at this vast sort of lukewarm equilibrium that the universe would fall into. But at the same time, it helped people recognize that living processes were somehow locally doing the reverse. That is, maintaining order when order tended to be exactly that sort of thing that broke down. I think that was both an important insight and a misdirection at the same time. And let me describe that briefly. It was an important insight because it made it clear that in order to keep living, in order for an organism or ourselves to keep going, to maintain our order, to maintain ourselves against this tendency of entropy to increase, we had to constantly do work. And to do work, physical work, generates more entropy. So that in a sense, there's this interesting paradox. In order to stave off the increase of entropy for my own body, for my own existence, I have to do work by producing more entropy in the rest of the universe. So in one sense, to stay alive, I like to compare us to a refrigerator or a freezer. You have to do a lot of work to keep the thing cold. So you have to do actually more work. The refrigerator, in running that motor, generates more heat in the world just to stay cold. And so it's a sort of thing that life does. But what's interesting about this process of living is that because of that realization, people began to think, and I think this begins at the end of the 19th century and on through the 20th century, began to think that all you really had to explain in explaining life was something that reversed the second law of thermodynamics, that seemed to produce order. What are processes that produce order? And the answer is that it's when the second law of thermodynamics is used against itself. The refrigerator is a good example of that. We're generating more entropy to keep entropy locally at a low stage. And that is to keep the temperature inside the refrigerator versus what's outside the refrigerator as separated. To keep it so that by turning off the motor, it'll go to equilibrium and that difference will dissipate. What caught my attention was that throughout much of the 20th century, it was thought that this was maybe the problem of life. All you really had to do was have a system that generated order by, in a sense, producing more energy. Now, in the late 20th century, we found lots of examples of this, oftentimes called self-organizing processes. Processes that by pouring energy through some system would keep it far from equilibrium. Classic examples that everybody knows about, for example, are whirlpools. In your bathtub, when water is draining out of the bathtub, what happens is a whirlpool tends to form over the drain. What's actually happening is that the water becomes much more organized. You get order production, as though it's going against the second law of thermodynamics. But it's doing this because it's, in a sense, draining the bathtub faster. By having the water more organized, it doesn't basically get in its own way. And so all of these processes that generate more order have this issue of driving towards the increased equilibrium faster and faster. Now, if life did this, it would be a problem. Because what has to happen is that life has to do that and at the same time not let the order dissipate. The key with a whirlpool is the whirlpool will disappear faster because it's draining the water faster. And this is true for all self-organizing processes. So my realization as I began to write this book was that the story of life, and therefore it's going to have to do with all order-generating processes that are associated with life, with mind, with purpose, and so on, are going to have to go one step beyond this idea of generating order. It has to, in a sense, not just generate order, but prevent it from disappearing. And that's one step further. And I realized that we really didn't have a science that helped us with that next step. That we were convinced that if we could just generate order, just be self-organizing, that would be sufficient.
Yeah, essentially what you've done is taken another step beyond a thinker I like a lot, Ilya Prigozhin, right, who came up with the idea that there's some pressure in the world, in the universe, for order to occur to the degree it allows energy to be dissipated faster. The whirlpool is a perfect example. Actually, convection in a boiling pot is another example.
Exactly.
The heat comes out faster because there's convection, and there's an example of corrosion, dissipative systems that organizes far from equilibrium energy conditions. And that is probably a part of what allowed life, but it's not anywhere near sufficient, as you point out.
Well, in fact, the problem is that when things get self-organized in this respect, they dissipate the very gradient that makes them possible. They speed up the elimination of what makes them possible. So, in effect, the key to life is that we have to use this process that seems to be self-destructive, self-undermining, and we need to use it against itself. So if you think about it, the self-organizing process is a process that uses the increase of entropy against itself locally by generating it elsewhere. For living processes, and from this I will also conclude mental-like processes, is one more step. You have to use this self-organizing tendency against itself to generate order and then maintain that order from destroying itself.
Gotcha. We're now going to dive into some of the deepest stuff in the book. And before we do that, we're going to hit on the definitions of some terms that you use, some of them from complexity science and philosophy, and some I think that you made up, but they were appropriate for the task. So let's start with emergence, a key term. My good friend, now deceased, Harold Morowitz, wrote a famous book on 27 layers of emergence or something, which I believe you referenced in there. And then why don't you tell the audience what, to your mind, emergence is?
So emergence has had a modestly long history back into the end of the 19th century. And it, interestingly enough, comes up really after the concept of evolution had sort of fallen into this special meaning. It's not just unrolling, but as Darwin began using it, it actually had to do with this process that generates the kind of adaptation that life has. And so that living processes evolve to become better and better suited to their environments. And as their environments change, they change to sort of track the environment, to become suited, to become adapted. And Darwin's theory of natural selection seemed to do a pretty good job of explaining that. One of the challenges of the theory is that it suggested that maybe the classic view that somehow there's a divine capacity that generates life, that designs life, could be replaced by a theory of evolution. And that evolution might cover this. I think it's still a misunderstanding of the concept of evolution, because ultimately the only things that evolve are things that themselves tend towards an end. That is, they are alive. Living systems evolve. Non-living things may simulate evolution, but they don't actually evolve the way life does. But as a result, towards the end of the 19th century, particularly in the work of John Stuart Mill, the philosopher, they began to worry about how what looked like discontinuous differences could evolve. Where evolution is about sort of continuous change, there were contexts in which sudden changes seemed to change qualitatively, not just quantitatively. One of those examples was the origins of life. Darwin famously avoids talking about the origins of life, and I think for good reason. It's not an evolutionary process. It's the process that made evolution possible. And so you can't talk about life evolving because life has to come from life, has to evolve from life. So the idea of living compared to non-living seemed to be a transition. John Stuart Mill was worried about what was then the new field of chemistry that was really developing, in which he began to recognize that two poisons, sodium metal and chlorine gas, come together and make a substance that is essential for life, salt. And he felt that the chemical transition from these poisons to something that's essential was an emergent phenomenon. That is, whole new properties came into being. Now, we understand that a little bit better now that we've understood that there's an ionic bond that holds the sodium and potassium together, and that when it's dissolved in water, they're not actually chlorine gas or sodium metal. They're something different. They're ions that have a different character. I won't go into the details of that, but this set up this question: could there be these sort of kind of sudden changes that were not evolutionary-like changes, but they cause these sudden differences? And the argument was that maybe such things as the origins of life and the origins of mind were so different from what came before them that maybe there was a different kind of transition at work. I think that that's probably right, but I think that we've unfortunately fallen into a kind of mysterianism about these processes. That is, they look so different, they look so qualitatively different, that it allows us to go back to this sort of mysterious, we can't know how it happened, it just sort of happened. It jumped, or that nature had it hidden for a period of time and then it emerges. And I think the term emergence had this sort of sense. We think about emerging from a cave, for example. That is, you're hidden for a period of time and it shows up. So there's a number of ways in which the term has this sense of something that was already there but not expressed. I think that that's partly right and partly misleading. So that what we have done in the end of the 20th century is recognize that maybe we could think about emergence differently. And it became more and more applied to things like we've just been talking about, the generation of order from disorder, from self-organizing processes. That seemed to be an emergence. Why did that seem to be an emergence? Well, it seemed to be an emergence because all the tendencies were going in the other direction. Suddenly, locally, we see that the direction reverses. That reversal is, in some sense, so sudden and so discontinuous that it seems to be a radically different kind of thing. And so it's you might say, qualitative change instead of quantitative change. Now, as I was saying just a few minutes ago, I don't think that accounts for the whole story, and certainly doesn't account for life. But life and mind were, again, these two features. And of course, when we talk about something like consciousness, it seems like something that doesn't exist, for example, for plants, maybe. Certainly not for rocks. And yet, there are two ways to look at emergence here. One is that, this capacity was always there, and it just emerges somehow. And you can take this in a number of different ways. One is that maybe everything's got a little bit of mind-like something in it, and that under certain circumstances, it emerges. It comes out of hiding, so to speak. You might say that it's a little bit like panpsychism, the idea that there's mental stuff in the world. It just only shows up when you've got the right kind of system. That's one way to think about the emergence problem. And the other way to think about it is that it actually has to do with new organizations of things. The story about sodium and chlorine and the emergence of new properties in salt is about properties that don't seem to have been there, but in some combination, they show up. Now, what's interesting about organization, about the new organization of sodium and chloride, is that, in effect, what's happening is it's the combinatorial relationships, the organization, that brings this about. The challenge is that organization is actually the absence of something, to go back to what I said at the beginning. That is, there are certain relationships that are no longer there, that are no longer realized. In sodium and chloride, you no longer have the ability for the chlorine atom to be separate in its normal state. You no longer have the capacity for the sodium metal atom to be in its normal state. They're recombined and changed in the process fundamentally, that you can't go back, so to speak. And I think that that's an interesting feature of the emergence process, that the organization that's there is an absence. It's something missing. And it's one of the ways that I sort of worked my way into this problem of thinking we've actually thought of emergence as adding something. And I asked the question, maybe we should be thinking about emergence as something being removed, and by virtue of its absence, something new is possible.
Great. In fact, okay, let's continue this in the context of about emergence and things like emergence. You use constraints quite specifically in this argument, which reminds me of, it's not quite identical to, reminds me of Harold Morowitz's use of the idea of pruning rules, that each emergence is the result of pruning rules, that chemistry emerges from atoms via the Pauli exclusion principle, for instance, right? And things of that ilk. So why don't you roll and let's try to keep it a little bit more brief, the idea of constraint with respect to emergence and things like emergences.
Well, I agree with Harold's use of it. I think that he, as a result, simplifies the transition. And the only difference we have in thinking about it is that I think that it has a hierarchic structure, that absences that make other absences absent also, in which you get this sort of hierarchic structuring. This is what I was about when I was talking about the transition from self-organization to living processes. There's actually a higher order kind of absence involved in this. I'll come back to this in a few minutes, maybe in our conversation.
Yeah, we'll get it. We have a whole section on that, so we'll get to that in a few minutes.
I'm assuming you will. So that basically the notion of constraint, I first encountered it reading the work of two different people. One is back in the late 1940s, Claude Shannon, the information theorist, used it to talk about the information channel and how information that becomes a message has to do with constraint on the possible variety of signals. That became his way of talking about what kind of a message, what kind of meaning was carried by a signal, though he didn't use the term meaning at all in his work. And the next source of it that really influenced me was Michael Polanyi, who wrote a very interesting piece that occurred in the 1970s, in which he argued that, in effect, what made living processes unique was that they were chemistry that prevented certain kinds of chemistry from happening, and that the key to living was to prevent certain kinds of chemistry, that the organization that emerges in life is the result of what's not being allowed, what's being prevented, what's being minimized. And he called that constraint, using this same term from Claude Shannon and from the cybernetics theorists of the 1950s and 60s. So in this process, what I realized is that constraint was, first of all, what's absent. It refers to what's not happening, what's not being allowed. But it's also the flip side of the concept of organization or form. A form or a symmetry is about certain variations, certain features that are not expressed. So if I think about, an ideal form like a triangle, it's about all the possible ways that this form could have been that are now not there. So I began to think that maybe the way to use the term constraint would be a better way than talking about organization or form. And where in the past we used form in a sort of positive sense, in a sort of Platonic sense, like there's this ideal that forms can be imbued in matter, that matter exhibits forms. Instead, that forms might be understood as what wasn't there, what features were not there, and that symmetry itself was a result of things being absent. That to just sort of reverse our thinking, not think in the positive, but to begin thinking in the negative when we talk about form. This allowed me to sort of rethink also things like even Aristotle's notion of form, which of course is influenced by Plato, that there's some sort of ideal out there. The advantage of using the negative is that now form is anything less than full variety, anything less than chaos. When some things are limited from being chaotic in their full variety of organization, of orientation, and so on, we say it's slightly formed. But this meant that there could be sort of this elaborate, almost infinite hierarchy of being more and more regularized, because anything regular, whether it's symmetry or a habit or a regular occurrence like a waveform, for example, all of these things can be talked about in the negative. And it's using the negative that helped me understand that, well, maybe using this term will help us get into this problem of life and mind.
Cool. Yeah, of course, the classic example is someone who described a sculpture as what was left when you took away the stuff from the block of rock, right?
That's right. That's right.
Classic example. Let's move on. This is all very good, but now we're going to get a little deeper here. I don't know if this is an invention of yours, but it's terminology I've never heard before, but it's very useful. And that is the distinction of orthograde and contragrade in the unfoldings of systems. Talk about that a little bit. In fact, unfolding as the systems is a little too narrow, but yeah, talk about those two concepts. These are pretty interesting.
So what we deal with all the time in the world, and Newton certainly, I think, sets us up in this respect. That is, there are processes of change that don't require any work, don't require any effort. The increase of entropy is a classic example. It's what happens when we don't do work. Things tend to fall apart. So if I don't keep cleaning up my desk, it gets messy. I have to do work to sort of keep it this way. And of course, this was the story about the refrigerator in life as well. Those spontaneously will go in some direction. Processes that happen spontaneously, processes of change that happen spontaneously, that is, they don't need to be pushed, I call orthograde. Orthograde meaning going in the direction that things tend to go spontaneously. In the years of the 60s and 70s, it was going with the flow, so to speak. If you're going with the flow of the river, you don't have to do any swimming. But if you're going to go against the flow of the river, you have to do a lot of work. And I call that contragrade. So grade referring to a gradient or a direction of change or an orientation of change. So orthograde is going with the flow. Contragrade is going against the flow. So in that respect, they're pretty simple. But what I began to realize is that this not only accounted for the sort of Newtonian version, that is to change something from an orthograde. So moving at a constant velocity doesn't take work. So we send this object hurtling into space at a certain velocity, and in empty space, it'll just continue, as Newton pointed out, until it runs into something or until something else works on it. To change that orthograde tendency, so in a sense, constant motion, constant similar velocity, doesn't take work. It's just what happens spontaneously. That's orthograde. Contragrade is what would happen if it runs into something else. Now, what's interesting is that what this means is that if another projectile hits this object that's moving in space and bumps it into a different direction, it's because their two orthogrades are not the same orthograde. And they each act contragrade to each other. So each of their velocities and directions, each vector of motion is now changed because they did work on each other. That's what I call contragrade. They are each contragrade to each other. And a contragrade means two orthogrades, two tendencies that simply are not aligned. So it's a way of, in the simplest physical sense, talking about work versus things that don't require work. But Newton didn't have a concept of the second law of thermodynamics. So when we talk about the process of generating order in a thermodynamic context, we're talking about a contragrade, something that's running contragrade to the second law of thermodynamics. So what I realized is that we didn't have a generic term for this going with the flow, going against the flow kind of thing that would work both for talking about just physical motion and energy and work, and processes that might have to do with thermodynamic processes. But then I realized it also has to do even with things like thinking. That is, daydreaming doesn't take much work, but trying to keep logically consistent about your thinking, trying to really figure out what's going to happen and what's not going to happen, or how to keep my thinking from being self-contradictory, it takes work. That there's a kind of orthograde and contragrade feature even to thought processes. And so I realized that we just didn't have terms that allowed us to talk about that relationship at all of these different levels. And that maybe that it would help us sort of unconfuse ourselves about these various features. It also led me to realize that we really didn't fully understand the very, very familiar term work, because we can now talk about work at many different levels.
We'll get to work in a little bit more detail later. Before we do that, though, we're going to get to what I hereby declare to be the meat of the matter, which is 3 layers of emergence, which you've defined. And I think I'm going to just let you take your walk through all 3 of them, because I don't quite know how to ask the questions to tease them apart. And that's homeodynamics, morphodynamics, and teleodynamics. And if you could use orthograde and contragrade in the telling of the story, I think the pieces will hold together a little better. I mean, this is, people, pay attention. This is the shit right here. This is what you need to hear.
All right. Well, so in one respect, because I had realized that we needed more generic terms to talk about these features. I wanted to then link these ideas to the concept of emergence and to get us away from what I thought were the ways we confused ourselves when we talk about emergence. So homeodynamic processes are basically processes that are orthograde, that tend to be happening spontaneously. Homeodynamics, by dynamic, of course, I'm talking about change. Homeo, meaning the same. So again, orthograde changes are homeodynamic because the dynamics does not change. The dynamic continues the way it is. And when we talk about homeodynamic processes, we're always talking about processes that, in effect, at the end, increase entropy or simply don't change, like constant movement of an object, a constant velocity and movement in direction of an object flying through empty space, for example. Those would be homeodynamic. That is, so the dynamics, in a sense, always tends toward homogenization, homeo. And that's, of course, what equilibrium is as well. What we find is that when a system reaches equilibrium, it's effectively no longer changing. It stays the same. Now, even a gas in a container that has reached equilibrium is in constant change. But notice that although the particles are constantly moving, the overall structure, that is the gradients, the constraints, the patterns, are going to stay the same. The system will stay at equilibrium. So it's reached a sort of a stable point. And there are lots of homeodynamic processes that also have that feature. So in one sense, it accounts for both, you might say, constant velocity of an object, homeodynamic, but also the constancy of a state like being in equilibrium. That is, an unchanging state. Those are homeodynamic processes. And what I realized is that there's going to be a set of order-generating processes that are of a higher order than this. In the case of self-organizing processes, we just a few minutes ago were talking about whirlpools, but the production of convection cells, regular hexagonal convection patterns in heated liquids and heated oil, for example, or the production of regular features like snow crystals, one of my favorites. These are all processes that, although they require homeodynamic processes to generate them, that is, there's an increase of entropy, there's a flow, there's a gradient in which energy is flowing through a system. One of the things that happens is that process generates order. So I use the term morphodynamic to talk about all of those processes that, by virtue of contragrade interactions between certain morphodynamic processes, and that they have to be set up in such a way that they exactly balance each other, counter each other, in a sense, that regularity shows up. Those are morphodynamic processes. They're processes that, instead of converging towards unchanging equilibrium, they converge towards regularization. Morphology, morpho. What I realized is that still, as I mentioned before, still doesn't account for the kind of thing that living processes are. And so using the same logic of juxtaposed homeodynamic processes that are just right, just balanced so that they produce regularity, could juxtapose morphodynamic processes. Processes that both produce order but tend to be self-destroying of their own basis for order production. If they could be countered to each other, balanced to each other, contragrade to each other in just the right way, would they produce yet a higher order feature? And so that what I realized is that maybe we could talk about end-directed processes this way, whereas each of these processes tend to go towards a stable state in which you maintain and reproduce and repair the order that tends to break down, has an end that is like the end of purpose, like the end of an aim of something. That is, it's not present, but when an organism gets, in a sense, infected or damaged, it engages not just in a process of making form, but of recovering the lost form, using processes that are form-producing to balance each other, to create new form. And that was something that doesn't exist. So that if the system is in breakdown, What it's doing is it's in a sense generating towards something that doesn't exist yet. When we reproduce, it's producing something that doesn't yet exist, but our whole organism is set up to produce that, as thought processes and living processes are always about that. And so the term teleodynamics, of course, came from applying the notion of dynamics, again, change, but change towards an absent end, an end that doesn't yet exist, an end that could be removed and then could be replaced, such as in repair or reproduction. And I realized that the same logic, building from two contragrade homeodynamic processes to produce morphodynamic processes, that there's another step in which two morphodynamic processes, two or more in fact, working together in a synergistic way, so they each produce each other's supportive and boundary conditions to sort of keep them from dissipating, could actually produce a system that was end-directed, directed towards its own existence, so to speak, and which is exactly what life is about. Life does work, is contragrade to its own tendency to go out of existence. Living things are working contragrade to the tendency that they have by their very life processes to use up the energy gradients that they depend upon, and therefore to go out of existence. So living processes are constantly finding new ways to keep that from happening. And those new ways, of course, don't yet exist at the present moment. They're still absent. So it became a way of talking about the very simplest notion of telos, of ends.
Okay, very good. And I think we should make clear, at least it was my read, hopefully I got it right, is that homeodynamics are pretty pervasive in the physical non-biotic world. Morphodynamics are rarer, and teleodynamics are rare as bumblebee fur. Obviously not quite non-existent, or we wouldn't have life. We'll get to that next. But is that more or less correct?
That is correct, yes. So what I would say is that the vast amount of processes of dynamics in the universe must be homeodynamic. That is, they're all running downhill, so to speak. There are special cases, and they're very special cases because it's not just any contragrade process, any contragrade relationship, but contragrade relationships that allow the buildup of constraints locally. That for that to happen, they have to be just exactly balanced. And that happens periodically, rarely, and precisely because they're self-destructive. They dissipate pretty fast. They disappear. So that self-organizing processes, unless they get frozen, like a snow crystal, for example, if they get frozen in a state where they can't dissipate, then they maintain structure for a while, but sooner or later that structure will dissipate. Living processes, interestingly enough, are the most rare in this respect and probably need very special circumstances to occur. But one of the interesting things about teleodynamic processes, because they are oriented to generate themselves and to generate similarities to themselves and to repair themselves, they're the only process that can actually amplify themselves, produce more and more and more, whereas morphodynamic processes just tend to wear out. So what I would say, in an interesting contradiction, that although teleodynamic processes are incredibly rare in the cosmos, when they occur and where they occur, they will spread and spread and spread like life has spread on the earth.
Very interesting. Now, for our next step, to make especially teleodynamics, which is a very abstract, at least it was for me, it caused my head to hurt a little bit till I figured it out. One of the things that helped me figure it out was your example of the autogen or autogenesis, which is, we'd be careful to caveat, is a story about what pre-life might have been like. It isn't the story, but it is a story, and it may have some relevance to it. But I found that an extremely useful way to get my head around the concept of teleodynamics. So why don't you tell our listeners what an autogen is in your model and kind of the process of autogenesis?
All right, so autogenesis, of course, means making yourself or actually bringing yourself into existence. And that's really what I'm about here. And what I wanted to do, and it's the development of this sort of model system, it's almost a thought experiment. The important thing about it is that I wanted an empirically testable thought experiment. So something that we could actually do. No one has actually done this, but I think it's set up in such a way that it is entirely realistic as a scientific project that one could do. But I wanted to be able to think about this relationship that I just described, teleodynamics, in concrete terms, so that I wouldn't be confused, so that I wouldn't be sneaking anything in. And so I tried to conceive of the simplest process in which morphodynamic processes were pitted against each other and supported each other. And that's what the autogenesis process is about. Autogenesis is, you might say, a thought experiment, but a thought experiment that could be realized molecularly. And it's because I come from a background of biology, chemistry, and physics, and so on, that I wanted something to think through this process that I felt was concrete and that I wouldn't be sneaking anything from under my sleeve, so to speak, an idea that was there that wasn't there to begin with. So here's how it works. What I used is two processes that we're quite familiar with in chemistry and physics, two molecular processes that are morphodynamic, that is, that are self-organizing. They produce more of the same, so to speak, so long as they're driven by a gradient. One of them is the process of catalysis, but actually it's not simple catalysis, where a molecule aids the generation of a chemical reaction that basically decreases the threshold for which this chemical reaction can take place. There's a process that's sometimes called autocatalysis. I like to call it reciprocal catalysis, in which one catalyst, catalyst A, generates a product, catalyst B, that generates a product, catalyst A. In this process, if there's enough raw materials that catalyst A and catalyst B can use these raw materials to generate these chemical reactions, A will generate B, which will generate more A's, which will generate more B's, to generate more A's and 1 B's until all the substrates are used up. Now, that's a self-organizing process. It's a morphodynamic process because it makes more of one form of molecule again and again and again and again. And so one of the things that happens in these sort of reciprocal catalytic processes like this is that locally the concentration of A's and B's will increase very rapidly, and the concentration of other molecules will decrease and decrease and decrease. Now, eventually, this is a self-undermining process, like all morphodynamic processes. It's self-undermining because it will use up all of its raw materials very, very fast, because it's a chain reaction. It's an acceleration. It's a little bit like a nuclear reaction in the sense that it's that every time you produce one thing, you produce two of something else, and it doubles and it doubles and it doubles and it doubles. So it's an accelerating reaction. It very rapidly uses itself up. So what will happen is that autocatalysis or reciprocal catalysis will eventually stop, and the A's and B's will dissipate away into solution. So it's a morphodynamic process that has all the classic features of a morphodynamic process. The other morphodynamic process that I focused on has to do with basically building crystals. Crystallization is morphodynamic. That is, it builds a regular form. And the way it does this is that you have molecules sort of in solution that if they fit together, they sort of lock each other in position. And in so doing, they give off a little bit of heat into the environment. Crystals form by virtue of being in a solution that's what we call supersaturated, in which molecules tend to come out of solution and tend to stick together and form these structures, these crystals. Crystals are regular. They have kind of a regular tessellation structure that we know as we talk about these repeated cells. Again, it has a kind of morphodynamic character. But crystallization, of course, only goes along until it uses up enough of the raw materials in solution that basically the rate at which molecules attach to the crystal lattice and detach from the crystal lattice are basically the same. It comes to equilibrium. The crystals stop growing. What I realized is there's an example of this in life, and it has to do with viruses. Viruses are basically DNA or RNA encased in a shell of proteins. And the proteins typically fit together because of their shape. They stick together and they form a lattice, but usually not a crystal-like lattice, but a sheet-like lattice. And these sheets fold in on themselves, make polyhedrons, and polyhedrons can contain things. Now, The issue in terms of the growing crystal, of course, it undermines itself. It only grows so far as it can. And a system that grows into a polyhedron this way will also close itself off and stop growing. But it will also slow down as it uses up, that is, its growth will slow as it uses up materials in its surround. And in fact, the growth will stop. What I realized is that one of the things that's happening in reciprocal catalysis is it's generating more and more of certain molecules. What's happening in this formation of a shell like this, a crystal-like shell, I'll call it a capsid. That's what we call the capsules that contain viruses. A capsid that's growing by attaching molecules to it. It uses up molecules and decreases the concentration of molecules. So reciprocal catalysis produces something that capsid growth requires. But the other thing that capsid growth produces is a constraint on diffusion. If a bunch of catalysts that in a sense interact together are, I'd say synergistic and codependent, as are the A and B in the reciprocal catalysis, if they can be contained, then they can't diffuse away from each other, and now the potential for their interaction is maintained. What we have now is that if the catalytic process generates an additional molecule, let's call it molecule G, that tends to be the molecule that forms a crystal-like lattice, a container, a capsid. That will be produced in more and more numbers in one area, along with the A's and B's of the catalysts. But that means that a crystal-like container, a capsid container, will tend to be growing where there's rapid catalyst production at the same time. And therefore, it will tend to fold up and capture some catalysts and keep them from diffusing. When the solution is beginning to run out of molecules to build a capsid, the catalysis is generating more of them, so it's keeping the speed of capsule growth at a high rate. And the capsule growth will occur most rapidly where there's the most catalyst generated, and it will produce a structure which I call an autogen. That is, in which the catalysts that are needed to generate the capsid and the capsid that's needed to keep the catalysts from diffusing away from each other will all be co-localized. It's in effect a self-reproducing virus at this point. A virus which contains DNA, which uses other cells to make capsid molecules and more DNA molecules. Now we have a system that, if it gets broken open by say it runs into something else or it gets heated up and heat breaks it open, the catalyst gets spilled out, but they begin to immediately make more catalysts and make more capsids. So the system tends to close itself back up again, to self-repair. This is a simple system in which two morphodynamic processes now balance each other out, keep each other from disappearing, but also keep their relationship between them from disappearing. So they each produce the constraints that preserve each other and support each other, and collectively produce a higher order constraint, which is the constraint of their relationship to each other. So you might say that they each have orthograde processes, orthograde tendencies, but their orthograde tendencies produce constraints which become, in a sense, the boundary conditions that make the other possible. So they're now contragrade constraints, but they're contragrade and supportive at the same time. And because of this, there's a third, what you might call formal constraint, or a constraint on those constraints, which is what holds the whole thing together. And that's, of course, what is maintained when the thing repairs itself. Now, if one of these is broken open so that the parts are distributed widely, 2 can form, maybe 3 can form, because all of these processes are related to each other in such a way that they're, in a sense, self-reinforcing or codependent. They're dependent on each other to maintain themselves and to maintain this higher order constraint. So the question is, what's getting passed on when one of these things breaks up into 2? What's been passed on? Well, one of the things that's happened is all the chemistry may have been changed. New molecules might now become capsid molecules. New molecules will become catalyst molecules contained in it. but the system of constraints will have been passed on. This is a situation in which constraints, absences, things that are prevented from happening, reproduce themselves. How something absent can reproduce itself. I realized that this was the very problem we were struggling with. How is it that something generates some relationship to something absent by itself? And it does so by virtue of the fact that this absence is effectively what we would call information. That what's being passed on is information about how to maintain the ability to generate this information yet again. That's something in the future that didn't exist. That's why it's teleological-like. It's not the basis for life or mind, but I thought it was the simplest version of what I was trying to get at.
Yeah, I found it very helpful. I mean, at first I was like, what is this? But then when you went through this example in the book in considerable detail, I said, I get it. Okay, this makes sense. And another thing that I'm just going to point out to the audience is this idea of kind of adversarial contragrade processes is analogous to, it's not the same, as the idea of GANs in AI, generative antagonistic networks,
yes.
where you have one network create a picture, then you have another network be able to produce something that's actually not the picture, but can be detected as if it were the picture. And that's how you can end up with like static that a neural net will say is a cat, because you've literally generated an adversarial process to try to beat the first one, which is kind of cool. So this is kind of that's an interesting analogy, that these kinds of opposing processes are generative. And I think that's one of the deep insights from this work, actually.
And if you notice that this is a relationship entirely described in terms of absences, but the key is that constraints are always embodied in something. That is, this is not a process in which nothing produces nothing. This is a process in which the constraints on forms, the constraints on tendencies of processes to take place, generate new kinds of constraints. And this is, so I like to go back and to point out that one of the reasons why reductionism sort of builds upon atomism is this phrase from Lucretius that ex nihilo nihil fit, nothing can come from nothing. What I'm saying here is that, in fact, there are certain relationships among absences that can generate new absences. So it's not exactly nothing, but absences can come from absences. New absences can be generated by relationships among previous absences. And that's, I think, the essence of emergence.
And that's indeed the, at least metaphorical equivalence to zero, right? If we don't see these absences, we can't think in the Deaconian method, right? Which, it's hard work to get there because we're not used to doing it. So let's move on a little bit. Time is marching. Let's do a brief touch on information. Tell a story briefly, comparing and contrasting Shannon information, Boltzmann entropy, and Bateson's ideas around information.
Good. Well, so Gregory Bateson was somebody who was very influential on my early work. And although I didn't spend a lot of time with him, I learned a lot from him and learned from his students and his writing. And so it had a significant impact on my thinking. But in many ways, I've recognized where he fell short. And part of my work was to sort of say, okay, what's next? What do you need to add to make this work? So I wrote a piece, really a two-part piece that now it gets modified in the book. I called this paper, it was actually two papers, Shannon, Boltzmann, Darwin, that basically talked about three ways that we use information and how they're related to each other. And it turns out that this is not an unknown relationship. People have been talking in these terms for a while, but haven't really paid attention to the sort of hierarchic relationship to each other. Now, part of it has to do with the way information theory was first generated in the late 1940s. Claude Shannon was actually interested in the engineering problem of sending information over a medium like telephone or radio or whatever. The medium has a certain flexibility. There's enough variation in that medium that we can carry forms within it. And of course, forms have to do with not allowing all the possible variation. Just noise is not very helpful. But if we can somehow sort of modulate the noise and constrain it a little bit, it's now possible to sort of convey some information. For him, information has to do with this relationship between the full variety of diversity of a signal and constraints on that signal. And so he was measuring what you might call how much of a message can be transmitted by virtue of comparing the possible variety that could have been received with the variety that was received. And so he came up with a measure of information, although it didn't refer to the concept of meaning or reference or aboutness in any respect. He was interested in the engineering problem. That is, how much information could be transmitted over a particular medium, how fast it could be transmitted, how much could be stored in a particular medium, and so on. As a result, information theory was generated in a way that was actually very useful for the sciences. It was useful because there was no worry about talking about the meaning of something or the value of something or what it communicated, what it was about. You could now measure the information in the genome by looking at, how many base pairs there were, how much diversity there was. You could measure an amount of information, the possible entropy of that system, as Shannon would call it, as how much variety could actually be there, and therefore what's the maximum amount of information that could be passed on. It was a nice quantitative measure, but as a result, it's now become useful in lots of ways. Of course, it's critical for everything we do electronically in information processing, whether it's computing or transmitting these signals over the airwaves as we're doing right now. In this process, however, we began to talk about information without talking about meaning or reference or usefulness. I realized that this was a serious problem. And beginning in the late 19th century, a philosopher named Charles Sanders Peirce, who also had a significant influence in my thinking, developed this field that was called semiotics. Semiotics was a discussion of basically all the ways things could be about things. That is, it's not just that the words I'm saying are about things, but also the pictures that we transmit have an aboutness relationship. Pointing is about something. The fever can be about the status of a body and so on. So paintings and pictures are iconic because they share formal features with what they represent. What he calls an index, like a fever, is physically correlated. It's a correlated relationship of aboutness. And words are about things, but they're not correlated physically necessarily, nor are they like what they refer to. They're linked by virtue of a convention about shared habits of interpreting. These are different ways, three distinctive canonical sort of ways in which things can be about. And what I wanted to do was to think, well, okay, what's the relationship then between information? And remember, from just a few minutes ago, I was saying that constraints may be the key to this. That's what's being passed on in this autogenesis process and maintained over time. But it's also how Shannon was measuring how much message could be carried. Had to do with what kind of constraints on the possible variety were there. So I saw that there might be a link between these. What I began to realize is that the beginning of quantum information theory, one of the insights that sort of drove this thinking was the idea that information is always in some sense also physical. Information is physical. Every medium on which we send signals from one place to another or store it is a physical medium. Whether it's a medium in terms of electromagnetic waves or pits on a disk or something like that. It's a physical medium. And that information, of course, is stored by the constraints, the patterning, the non-chaoticness in that medium. What I realized is that that meant that what Shannon called entropy was his measure of, in a sense, the full variety of something. That's like physical entropy at equilibrium. But if all information of Shannon's sort has to be embodied in a physical medium, then in fact, the physics of that medium matters a lot. And what that means is that the Boltzmann entropy, that is the increase in physical entropy, actually is part of the problem of information transmission. When we find noise in a signal transmission, it's because of, in a sense, the Boltzmann effects of the physical entropy of that medium. That medium is degrading over time. It's losing constraints. So if constraints are carrying the message, and there's a process that interferes with it, the second law of thermodynamics, because it's a physical medium, then in fact we're losing it. That's noise. But the interesting thing is the distinction between noise and signal is not intrinsic, in the sense that if I'm a repair person looking at a computer that's producing random bits on my screen, that's noise to me, but the repairman sees that as a signal, as information about what's wrong with the computer. So that the distinction between signal and noise is not a distinction that tells you which is actually the information, which is the meaningful part. And I realized that this was the link between Shannon and Boltzmann. And in fact, this is where contragrade and orthograde come back into the picture. So in the sciences, one of the things we look at is that when we see some feature of the world that is constrained, that is not in its most probable state. The most probable state is the one in which it's run down, its orthograde processes have come to a stable state. If we see something that is not in its most stable state, it's in an unusual configuration, it immediately tells us that medium, that constraint, tells us something about the work that put it there. The work is no longer there sometimes, but we infer it as happening beforehand. That is now the structure of a snow crystal. When I look at it, when a scientist tries to study how it was formed, he's asking the question, what work produced it? It's now carrying information. The constraints of its structure, the symmetry of its structure is information about the Boltzmann process, the process of work, and how a morphodynamic process produced it. That's information. Science is based entirely on this process. But now here's the interesting feature. To assess that, you need a process that sees that far from equilibrium system and is interested in how it was produced. What's out there? What is it representing? It actually represents in form the work process that generated it. So to interpret it, to use it to be about something that it's not, to have the snow crystal to be about a process that it's not, that is this process of work, of heat dissipation that produced it falling down through the atmosphere. There has to be a process that is interested in, you might say, is organized in such a way that it's using that form to get at something that's absent, that's not there any longer, that's represented in it, the concept of a representation, in effect. And that's what the Darwinian process helped deal with, and the origins of life is about. This is why it became Shannon, Boltzmann, Darwin, or Shannon, Boltzmann, Bateson. And here's how Bateson fits into this. Bateson, looking at Shannon's information theory, said that we can think about information as a difference, a constraint, that makes a difference. So he was using the example at the time, basically a cybernetic example of a thermostat. A difference in temperature which causes a difference in the expansion of a bimetallic strip that orients a switch. In his case, it was a mercury switch, so that it turns on a machine, in this case, say an air conditioner or a furnace, to change the temperature of the room, which changes the twist of the bimetallic strip, which changes the switch. A difference in the temperature makes a difference in the metal, which makes a difference in the switch, which makes a difference in turning on the furnace or the air conditioner, which makes a difference in the temperature of the room, which makes a difference in the bimetallic strip. A difference that makes a difference, but in a sense transmitted around. This was his notion of information, but notice that this is a purely physical process. There's another way that I realized that Bateson's phrase, a difference that makes a difference, if understood in the English language, has a kind of double entendre. Because in English, to make a difference means to matter. It's not just to change something. So it's a difference that matters. The question is, under what circumstances can some difference matter? Well, something matters is if that something is necessary to keep existing, to keep doing this. Living systems have to understand the world in terms of what matters and what doesn't. What aspects of the world are useful for its self-maintenance, self-persistence, its future generation, and what is not. Systems that are teleodynamic distinguish the world into self and other, things that are supportive and things that are non-supportive, things that are dangerous and not dangerous. For non-teleodynamic processes, there is no self to maintain, no future to generate. And as a result, there is nothing that we would call a normative character. Normative referring to things that are good or bad, right or wrong, true or not true. Those are features that only take place if there's a future-orientedness and a self-other distinction. Teleodynamic systems and teleodynamic processes have those features. Living processes do. The Darwinian process is all about fitting with the world, identifying what aspects of the world are useful, unuseful, ignorable, or avoidable and dangerous, breaking up the world into these sort of normative features. And so what I realized is that in order to interpret, you needed to have a teleodynamic process. You needed to have something that both had a self-other relationship and was a self organized around constraint and absence. Because it was only constraint that can be about something else, some other constraint. Therefore, the constraint that we see in the snow crystal can be about the work that's out there. So what we see in the world is that organisms are all about looking for things that are either dangerous, that is, they exhibit the constraints or the lack of constraints that we need to avoid, or they exhibit the constraints that are useful and available. And so having discernment becomes a critical part of this process. That's what the Darwinian process gives us.
Right. Very good. Now, you managed to hit on my next two sections, which was work and the Darwinian natural selection and how it worked with your theory. We could go into a lot more depth, and there's lots of good material in the book, but in the interests of getting through to where we need to get to, I'm going to skip those. So let's go next to sentience. And you use sentience in a very broad sense. So why don't you tell us what you mean when you say sentience and how it leads us towards us eventually?
Right. Well, so let's go back to the autogenic problem. In order for a simple system like that to persist, it needs to be within an environment that is supportive. In an environment that's non-supportive, it needs to be, in some sense, able to defend itself, to react in such a way that it's non-influenced by that environment. The result is that these closed systems that are like a virus, like a self-reproducing virus, can actually persist in relatively unsupportive environments. This is how viruses today get passed on. They're relatively inert. They don't need to interact with the world much. And as a result, they can sit on the surface for long periods of time. They can be desiccated and a variety of things. The simple autogenic model that I described is one that can persist and stay whole, stay far from equilibrium, not break down in a whole variety of environments long enough so that it might be able to diffuse into an environment that's a little more supportive. In fact, where it forms is an environment that is using up some of its raw materials. So it's best to sort of be quiescent for a while and let diffusion sort of move it around to somewhere else and to rebalance environment. What I realized is that we could talk about the autogenic process that was, in effect, aware of its environment in some sense, in the very simplest sense. And let me give you a sense of how that might work. If the surface of this capsid this container, this virus-like capsule, had shapes on it that tended to allow useful molecules to stick to it. And when they stuck to it, it weakened it. So that if you had precursor molecules to the catalytic process in the environment, more and more of them would stick to the surface and weaken its containment. And if enough of them were there, it would tend more easily to break apart. But notice that under those circumstances, it would tend to break apart in exactly the kind of environment that would allow it to form back together very quickly and easily, an environment that had lots of raw materials in it. If it was much more stable in an environment where nothing was sticking to its surface, it in effect would be able to resist breaking open more effectively in hostile environments or non-supportive environments. In this respect, it would be sensitive to environments that are good for its persistence versus bad for its persistence. Now, this sensitivity is, for me, the simplest notion of sentience. It's aware of its environment. Now, not in the sense that you and I are aware, or even that a plant or a bacterium is aware of its environment. It's simply organized to be differentially reactive in terms of its environment, reactive in a way that maintains self, that avoids damage, that increases the probability of also passing itself on, making more copies of itself. It's now divided its world into what's good for me and what's bad for me. Even though there's no knowledge of it, it's sort of built into the system. But it's built into the system because of its teleodynamic nature, because it is organized around the future possibility of maintaining itself. It's organized around the tendency to react against what would tend to break it down. And for this reason, now it can be organized in a very simple way to be sensitive to its environment. So the word sentience, which we normally sort of reserve to talk about creatures like us that maybe even have nervous systems, I wanted to say, no, there's a much broader sense that we need for it. This is a case in which I might have come up with a neologism to talk about it, but I couldn't think of one. And I thought that sentience might be good. So I said, but this is a little bit like the sentience of plants. Plants don't seem to have a complicated representation of their world, but they react differently to their world. Their roots go towards useful parts of the soil where there's the right liquids, the right amount of water, and the right amount of nutrients, and avoid other areas. Leaves tend to grow towards where the maximum light is, and so on. They are growing in a way that are generating themselves with respect to their environment. That's a kind of sentience. So I wanted to say that maybe we should just divide these things into what you might call vegetative sentience, and maybe the sentience of the autogenesis process is even simpler than that, but it's a little like vegetative sentience. And then there's the kind of sentience that involves also a full representation of the possibilities. That's what brains provide us with, and I like to call that subjective sentience. I'm not sure that this is the right division. There's maybe more divisions of sentience here, but it allows us to recognize that even something simpler than even the simplest bacterium, as simple as a virus, and maybe even simpler, can be reacting to its world, can be organized to divide the world of other, not itself, but the world out there, so to speak, into positive and negative, normative. So this is the transition from what you might call chemistry to normative chemistry. Chemistry that's good or bad, chemistry that's right or wrong, chemistry that works in the correct direction or not. But it's only when you get subjective sentience, when you get sentience that creates models of the world, that you can now have true models or false models. It's a little more complicated, and it requires a new level of emergence. So the distinction between subjective sentience and vegetative sentience, I think, is also an emergent distinction.
And that's where you start getting up to consciousness. And we've had many, many, many shows about consciousness. And we always know that
people define it differently. And, from people who are convinced a rock is conscious. Christoph Koch, very distinguished scientist, right?
Yeah, that's right.
And there are other people who say only humans are conscious. Even, an ape isn't conscious, or certainly not a dog. And I go, seems like bullshit to me, but hey,
Yeah.
right? So let's try very briefly to frame the line where you think consciousness begins.
So the first thing I want to say is that we make a great error in thinking that we're going to solve that problem without solving the problem of sentience. So the problem I just described, and why you, I think, rightly bring it up first, is that until you understand what sentience is, even in its simplest form, why it's different than what a rock does, and what it is about the organization of the process that makes it different, then you have no possibility of dealing with such a complex, high-level problem as consciousness. So, with Descartes starts at the worst problem that he could possibly start with, the problem of what's different between my experience and chemistry and physics. We're stuck with that. So there's two possible non-solutions to this. One is the solution you just mentioned, which can be called panpsychic or panpsychism, or sometimes it's called dual aspect theory. Dual aspect refers to the physical aspect and the mental or psychic aspect of things in the world. That maybe every electron interaction has a kind of psychic aspect to it. There's another way to say it, and that is that no, consciousness itself is an illusion. It's not real. I've always, whenever somebody says that to me, I want to ask the question, well, who is having this illusion? To have an illusion, you have to be sentient. You have to recognize that it's not real, that it's an illusion. You have to have a representation of something. So that, in effect, I think both of those are non-starters. The question is somewhere in the middle, obviously. The question is, how does sentience become more complex than what I just described in terms of this, what I sometimes call the sensitive autogen? It's sensitive to its surface. It's a discerning autogen, so to speak. That's a process that we have to see as the beginning of this, because what can happen is this is what makes evolution possible. The key question is that what makes a creature with a brain different than a creature without a brain? Creatures without a brain, like most plants, are sentient in the way I've just described it, but they're not sentient in the sense of having a representation, a model of what the alternatives in the world are, what the possible things are out there. It's immediately reactive to the world. Now, it's still sentient, but it's not sentient in the complicated way that animals with brains, particularly with complicated brains, are. So, now, the good news in this with respect to my perspective is that I actually began my career studying brains. Most of my career was in neurosciences. So it was obviously, for me, a problem of figuring out, no, not how to evade the question, but how do we actually come at the question directly? And the first thing is to begin to understand how sentience can become more complex. I don't think it's a difficulty to understand how the sentience of a virus can become the sentience of a bacterium. The difference is that a bacterium, of course, has all kinds of energetic processes. It can actually carry energy in and of itself, and it can do things of itself, even if it doesn't have enough energy coming in directly from the world. Where the autogenic virus kind of model of the autogen is one that needs to be changed from the outside world. Life goes through a process of figuring out how to sequester its own energy for periods of time so it can do things when there's not enough energy in the world. It has to replenish this. It has to eat, so to speak. But eventually, it allows it to have more agency in this respect. It's not just passive agency. It's not just agency that distinguishes things in the world. It's now agency that can actually seek it out and seek out alternatives to move around when it's not getting what it needs, and so on. What we see is that, of course, that kind of motility, though you're rooted to the ground if you're a plant, the fact that your roots have mobility, that your leaves can be oriented, that your pollen can be blown around or carried by insects, motility is there and setting things up to take advantage of it. But when you have to move yourself from place to place, you need to be able to predict. So when we see organisms animals that are sessile, that attach themselves to someplace, or very seldom move around, oftentimes they have distributed nervous systems. So think about jellyfish, which can sort of move themselves a little bit, but they don't go in any particular direction. They don't find out where the best light is, where the best water is, where the fewest jellyfish are, where the most jellyfish are if you want to reproduce. The same thing is true with creatures that are rooted to the ground, like sea anemones and so on. They have some abilities to move their tentacles and so on. But once you're rooted to the ground, you don't really need a brain. You can have a distributed nervous system. But when you have to move from place to place, you have an interesting problem. You have to predict. You have to see what's ahead of you, so to speak, or sense what's ahead of you. What's not immediate. What is not immediate is what's absent but could be. It's a potential out there. But if you have to move to it, basically the thing that's doing the prediction has to be at the opposite end of that which is doing the propulsion. And so what we find is lots of animals have developed a bilateral symmetry, in which they have at one end a whole lot of sense devices that are getting information about their world, and at the other end they have propulsion. They have a head and a tail. And at the head, because that's where you're doing all the prediction, that's where you want all the informational processing. You want to have something that can actually do that prediction. So it's not a surprise that brains develop at the head ends of things. And there's a tail end of the things where you get most of the production, you dump your wastes, maybe you do reproduction down there, but you use the head end to figure out what's in the future. So the key is that brains develop, whether in insects, in snails, in worms, or in vertebrates like ourselves. You develop a chunk of nervous system at one end that's about making prediction. In fact, the main predictions are oftentimes using light or sound or chemistry, which are pretty good predictors because they turn out to be ingredients, and distance information can be sort of predicted from this. What's interesting about this process is what the nervous system actually is. Now, first of all, the body itself without the nervous system is teleodynamic. It's teleodynamic because it has all these features that we just described before, maintaining itself, and maintaining itself with respect to the environment. But if you have to maintain yourself with respect to possible environments, an environment that might not be located here, but might be located somewhere else, then you need something more than that. And I think the key is that nervous systems are, in effect, micro-teleodynamic processes within a larger teleodynamic process that they maintain. It's a teleodynamic process of a teleodynamic process. It's a nested teleodynamic process. Now, what is it about teleodynamic processes? They're predictive processes. They're processes that generate a self-other relationship. And they have a particular dynamical structure. That's the structure of this contragrade relationship between morphodynamic processes that creates a unity, this self versus something else. And it's once you have that kind of unity that you can now do interpretation, that you can now have a relationship to something that you are not, and that you can discern the difference between things that are out there that you are not, distinguish good things and bad things. That's what the nervous system does. But notice that it's a teleodynamic process of a teleodynamic process and about the teleodynamic process that it's a part. It's in effect a teleodynamic process made up of a teleodynamic process. In a sense, it's a nested teleodynamic process. It's a teleodynamic process of teleodynamic processes. And this is why it's a higher order teleodynamics. It's not just the simple sentience that simple teleodynamics produces. It's a teleodynamics with respect to teleodynamics.
And as I was reading this, my takeaway was that what to me seems a lot of confusion about the relationship between neurons and mental phenomena can start to evaporate when you realize that people who try to make that mapping are missing at least a couple of layers, and probably more than a couple of layers of emergent dynamics. Is that what you were trying to point to?
That's exactly what I'm trying to point to. In fact, my point here is that every neuron, every cell in the body is teleodynamic, in a sense, trying to maintain itself. Neurons are trying to maintain themselves while being disturbed by other neurons. They're trying to keep their metabolism from running down, taking in new energy, and being forced to sort of kick out signals that require work. They are maintaining their own teleodynamics, and yet they're now organized into a network. The network itself has a teleodynamic structure. And one of the things I began to ask myself was, okay, how is it that neural dynamics, that is the communication that's taking place between all of these neurons with respect to how they're relating to the body that they're a part of and the world that they are relating to the body that they're a part of, how is neural process teleodynamic? And that caused me to rethink all the neuroscience that I had actually been trained on, had been studying most of my career. How is it then if teleodynamics is made up of homeodynamic processes that are contragrade to each other and morphodynamic process are produced from that, and teleodynamic processes are made up of these interacting morphodynamic processes? If the sentience of the brains is teleodynamic, there must be corresponding homeodynamic relationships, morphodynamic relationships that actually produce this dynamics that we call cognition and eventually consciousness.
Yeah, that was quite a new idea for me. If I read it right, was that modulation of thermodynamics may actually be an important part of the regulation of mental phenomena.
In one respect, you mentioned at the beginning of our conversation, Tony Damasio, who you've introduced. One way that we overlap completely is to recognize that it's not I feel because I think, but I think because I feel. That is, feeling is primary. Everything about cognition is feeling. Yes, some feelings can be about, but feeling is the very, very basis of this. That's what we mean by sentience, by sensing something, by feeling something. And the key to this, for me, is to recognize that feeling is about work. When I feel something, it's because of a contragrade relationship. That's a work relationship. Feeling is about something that was spontaneous being disturbed. When something wakes me up, it's because something that just sort of happens spontaneously now disturbs that spontaneous process. Work is being done on my nervous system, and it's responding to it. And that means that we need to begin thinking about the nervous system not just as computing, not just as running signals around in some form, but actually understanding how signal processing in the brain is about its own teleodynamics. It's about its own morphodynamics, and it's about its own homeodynamics. And the term emotion, for example, is wonderful in this respect because it actually captures the notion of motion, of inertia, of this tendency for things to run in a certain direction. When somebody suddenly startles you, it has this sense of interrupting, of blocking you. It's like work was done. And your emotions have a kind of inertia. You can't immediately shut them off and sort of move to something else. Thoughts have a kind of inertia. Our freewheeling, sort of daydreaming theory of mind kind of experience takes very little work. But when we want to do something, we have to do work. We have to stop that tendency. We've got a nervous system that tends to be very homeodynamic at the level of generating aboutness, of generating new information. It's homeodynamically doing this because, again, it's a teleodynamic system of a teleodynamic process. It's this sort of nested teleodynamics within teleodynamics, in which the teleodynamics of brains is about the teleodynamics of bodies, which is about the teleodynamics of keeping brains going. So it's this complicated, you might say, higher level teleodynamics of teleodynamics. Teleodynamic processes are now pitted against each other and reinforcing each other in the way that morphodynamic processes balancing each other produce something. So my point here is that it's a higher order mode of teleodynamics, moving into this kind of sentience, what I like to call subjective sentience, has this feature. And it's a different kind of sentience We recognize it differently because now it has to be a sentience that actually represents absences. That's what we're really good at. Representing the world that could be, that was, that might have been, that can't be. You can only do that, I think, with this level of teleodynamics of teleodynamics.
And using that as your model, and explains why maybe we're missing some things here and how the brain works. Now, one of my areas that I study, at least secondhand, is attention. What does your approach say about the nature of, let's just use humans to keep it simple, human attention, because that's something we all understand at least a little bit.
We all experience it. Whether we understand it is another question.
Good clarification. So what does your approach say about attention? What is it?
So attention is obviously takes work. When I attend to something, either something has forced me to attend to it. Pain is a good example of this. It's forced me to do certain kinds of work because the damage that's being done, or potential damage. Things that are, somebody's arguing against me in a discussion. It's a kind of, I have to do intellectual work because it's beginning to become contragrade to my own thought process. So I work to sort of figure it out, to work against it possibly, or maybe to work out a synergy in which they work together to produce something more. So attention, we always experience it in terms of work. It takes effort. And I like to point out that when we ever talk about effort, there's a contragrade feature associated with it. So how do we think about the contragrade process of the nervous system? And I think we have to think, this is why we have to abandon our familiarity with computing as a way of thinking about nervous systems. Of course, computing, there's no one home because computers don't feel. Computers aren't doing anything with respect to maintaining themselves. On the other hand, nervous systems are all about maintaining themselves and maintaining the bodies that they're parts of. So the fundamental thing that nervous systems are doing is about self and other, just keeping this apart and maintaining one part of it, and doing so with these predictions. But that means that when something is a threat to that teleodynamics, work has to be done. The nervous system is set up to begin to initiate that work, for example, with respect to pain or something else, or with hunger when we're running out of fuel. It starts to do work. But in fact, the physical work that the body has to do with respect to hunger is sending a signal to the brain that says, now do neurological work. The experience has to be attention. Work is always something spontaneous in response to something else spontaneous, to orthogrades that are not moving in the same direction, you might say. As a result, attention always has this feature. Either there's some spontaneous process, I'm daydreaming, and now I've decided I want to think about something in particular. This thought brought something up. I need to do work to suppress this spontaneous tendency. The question is, how does that work take place? And this is why I think we need to rethink what the nervous system is doing in non-computational terms. Now, let me go back to put it in the homeodynamic, morphodynamic, teleodynamic framing. What is a representation in the nervous system? The computing model says it's a bunch of switch settings. It's a state of something. But a state is not what a representation is. All the representations that you and I are involved in, all the conceptualization and the experiences are processes. There's something dynamic. Thinking is a dynamic process. Feeling is a dynamic process. Representing is a dynamic process. It has a physical basis. There are structures underlying it that bias and constrain these processes. But experience, attending, experiencing, responding, feeling pain, all of these are dynamics. It's like a flame. A flame doesn't have states. A flame is a process intrinsically. Thought, mentality is a process. And even when you're asleep, it's a process. It's continually happening. The question is, so what kind of a process is a representation? What I would argue is we have to think about it again like we were thinking about homeodynamics, morphodynamics, and teleodynamics. It's a form, a representation has to have a form. That is, there has to be some process that generates regularity, that generates constrained dynamics, that has a shape, so to speak, a symmetry. The key then is that a representation is not a particular state in the brain. It's, in a sense, playing a kind of melody, you might say. It's more like music. Representation is a particular kind of melody, a particular kind of activity in the nervous system. But notice that to generate form in a system that is spontaneously just using energy, spontaneously generating what you might call background neurological noise, work has to be done by driving metabolism against the metabolism that's just producing noise. There has to be a contragrade process that produces now form, dynamical form, morphodynamics. So what that means is that a part of the nervous system that is, for example, responding to inputs to interpret that input as a particular visual shape, for example, has to be generating a dynamic, has to be generating a dynamical form. That is, the representation is not a set of static states, not a set of switch settings or synaptic weights. It's the dynamical activity. It's the morphodynamics of that region of the brain that has a particular dynamical activity. I think is much more like music than is like computing. But what that also means is that morphodynamics is now going to be pitted against or with the morphodynamics of just maintaining the brain and the body. Just the background activity of maintaining self and equilibrium. That means that every perception or every time that I shift attention to some particular feature or form or memory even, that's a process in which two morphodynamic processes, the morphodynamic process that's part of maintaining stable self, and the morphodynamic process that is coming in from the world, for example, that I'm responding to with respect to the world, are now having to be balanced against each other. That's a higher order teleodynamics. That we actually experience ourselves when there's a tension. We experience ourselves at the moment that we're generating work to generate morphodynamics with respect to the work that we're generating morphodynamically in the interpretive process. And when they become in balance, first of all, in relationship to each other, which is a little bit contragrade, what we're doing is, of course, we're trying to resolve that contragrade, trying to resolve the representation. How do my needs, how do my interests, how do my desires map with what's coming in? How can I make best sense of it? I'm actually pushing that system towards teleodynamics. That it's a process of, teleodynamics is a process of coming to this unity. One of the things that we try to do when we try to interpret something or understand something is we try to make it unconscious. In many respects, conscious effort and attention is a process in which we're trying to make things unconscious again. When it's unconscious, it's okay. It's working just fine. I'm unconscious of most of what's going on in my body because it's working just fine. One of the things that consciousness is about is making things unconscious.
Yeah, so we know, like when we playing sports, right? If you're thinking about playing tennis, you suck at playing tennis.
Absolutely.
Only when you get it down to the automatic stage do you actually become a decent tennis player.
That's right. And notice that this is true about everything in our experience. When was the last time today that you were feeling the constrained feeling of your toes inside your shoes? That information was continually going up to your brain. It was continually there. It was always there. But we weren't aware of it because the brain was saying, oh, it's more of the same, more of the same, more of the same, more of the same. It's iconic. It's not difference. It's not a difference. It's a difference that doesn't make a difference. To use Gregory Bateson's phrase against itself, so to speak. Our brains are constantly taking in that information. It's constantly there, but it's in morphodynamic balance with the rest of the morphodynamics. It says, okay, yes, I'm generating a signal that expects it. The brain is constantly taking in this information, constantly getting information from my toes. But it doesn't make any difference. When the air conditioner in the room suddenly shuts off that you weren't listening to up to this point, suddenly you notice there's something missing because your brain was constantly expecting it. But in that expectation, one of the things that's happened is we're not conscious of it. So I like to think of consciousness as a process to try to destroy itself. Consciousness is a process that's trying to undo itself all the time, trying to make things unconscious. Why? Because you can't be conscious all the time. You've got to resolve this. You've got to set things up. You've got to adapt moment to moment, second to second.
And also, of course, the actual processing bandwidth of consciousness is pretty small. I've read estimates as low as 50 bits, right? And so if you're going to do more than 50 bits of work, you better do most of it unconsciously or you're not going to get much done. Think about if you had to consciously pick up your foot and move your leg and unflex your knee every time you walk down the street. You weren't going to make very good process that way. So yeah, I love the idea that the job of consciousness is to make consciousness go away and only to use consciousness when you have to. I like that. That's very, very useful.
So think about it in terms of the sentences that I am now producing. If you had to produce word for word these sentences, just in a couple of seconds, just in a fraction of a second from now, it would not be possible. Yet you are conscious of every sound, taking it in, and you, as quickly as possible, took that information, that sound information, turned it into something else, something that extends over the 30 seconds of this last bit of conversation, so that it all fits together in a whole if you're doing a good job of the interpretation. You have made most of the rest of that unconscious as fast as you possibly could, precisely because we have such a tiny bottleneck that we can keep track of, and we can't do many things at once. So we have to sort of push it to this other level as fast as possible.
Very good. One last thing here. We're coming up on our time limit. In fact, both of us have to go here. I think we share a sense that the hard problem isn't as hard as some people think it is. Though I don't have much to say other than instinct, you actually have some things to say about that. For our audience, why don't you state briefly and concisely Chalmers' hard problem, and what does your work, what light does it shine on the hard problem? And after that, we'll call it a day, because a lot more we could talk about here, but let's end on this one.
Okay, it's a big one. So the hard problem, of course, is a problem that goes back to Descartes and others. That is, why is the experience of being you and I, the sentience, the consciousness, so unlike all the features that we see in the rest of the world, in the physical world? The hard problem suggests that, the more and more I learn about how the nervous system works, I analyze how synapses work, I analyze how neurotransmitters work, I analyze how this part of the brain is active when something is going on, and this part of the brain is active when something else is going on. The hard problem is that the more of those details I get and I can describe, it doesn't ever seem to describe my experience. The idea is that though I approach this further and further and further and get more and more information, it doesn't ever seem to cross this threshold. I began my book that we talked about with the Zeno's paradox. Notice that this is very much like Zeno's paradox. The more and more we know about the brain, the more and more details we get, the more and more we subdivide this out, the more and more halfway we get there, and halfway we get there further, and halfway we get there further. We're beginning to look at the molecules and the synapses and so on. We don't seem to reach the target. We don't seem to have any better understanding of why it feels like this. The hard problem then suggests that maybe all of this scientific work is, in a sense, not getting us any closer. The hard problem is that maybe it's a fundamentally different kind of thing. And the hard problem is that, well, maybe it's hard because we can't do it by science. Because maybe it's beyond science or before science. And of course, that is ultimately a version of Descartes' dualism. That mind, which is extensionless, according to Descartes. It has no width. It has no solidity. That mental processes don't seem to be stuff in the right way. He calls this something that doesn't have extension in space and time, whereas everything physical has extension in space and time. So he uses the concept of extension to distinguish this, and therefore makes the claim that, of course, the two are completely separate realms, that you can't cross these realms. Eventually, that's what David Chalmers' argument is about consciousness. It's a version of this, but in which he's now sort of amplified it by saying, look, all of this science about how the brain works has not gotten us any closer. It's not going to get us any closer. No matter how much we know, we'll never get to the target. No matter how far the arrow travels, it's always got a little more to go before it hits the target. That's why it's like Zeno's paradox. But Zeno's paradox was resolvable just by rethinking the concept of zero, of absence. So that's part of what motivated me in this story. But again, notice that what the story that I've told is all about. It's about these systems of constraints, how constraints make new kinds of work possible, and how new kinds of work make it possible to produce new kinds of constraints. And constraints are what define form and absence, and as I've shown, ultimately define telos, end directedness, ultimately define representation and aboutness, normativity. My point here is that, in fact, we've been looking at the wrong side of the story all along. What makes it seem like it's the hard problem, that it's the impossible problem, is that we've been thinking that just have to do more physics and we'll get it right. Just have to look at more stuff, more energy, or maybe look at the quantum world, and the quantum world will get it right. That because the quantum world has got all this mysterious stuff and consciousness is mysterious, maybe the one mysterious thing will explain the other mysterious thing. My point is, no, we don't have to go that way, but it requires an inversion of our thinking. We need to begin to recognize that absences matter. They make a difference. And they're the only thing that makes a difference in that sense. My way of thinking about how the brains work, it's not the synapses, it's not the signals. It's the dynamics. The dynamics defined by the constraints that they carry and that they juxtapose and that they synergistically link with each other. It's the absences. And that means that you and I, and what we are, everything about us is with respect to what we are not. We're not the physical stuff. We know this because the physical stuff gets transferred day to day, year to year, moment to moment. The physical stuff that made me up when I was 1 year of age is not the physical stuff that makes me up now. We are not the physical stuff. We are not just the pattern, not just something stable. We are this dynamical system of constraints that keeps itself in existence. Constraints that constrain their own existence or constrain their own tendency to not go out of existence. The difference between existing and being means that it's doing. This philosopher Hans Jonas said that, that life is always doing, that being is doing. That's what we're talking about. But doing is work. And work is always the exchange of energy, the breakdown of gradients of energy in a constrained way. You can't do work unless you constrain the dissipation of energy. But by doing work, you can generate new kinds of constraints. And if you have new kinds of constraints, you can do new kinds of work. And if you can do new kinds of work, you can produce new kinds of constraints. That, for me, is the essence of the emergence problem, and why the very essence of what we are is an emergent process. Because we're constantly producing new constraints. The fact that we're talking on these devices is because we've taken what you might call rare earth metals from all over the earth. We've concentrated them into unnatural concentrations, mixed them up in exact combinations. We've constrained the distribution of these materials in such an extreme way that it's capable of doing work that wasn't conceivable 1,000 years ago, could not even have been predicted 1,000,000 years ago. Probably human life, human cognition, human morality, human ethics was not in the cards in some way, was not just hidden a million years ago, but had to emerge. Absences, new absences coming into existence from old absences. New absences are fundamentally new, fundamentally different. That's the emergence story. And so what I'm trying to say is that you and I and our experience is because we're on the side of those absences. We are those absences. So, I suppose you could go back to Buddhism and say, maybe Buddhism had a hint of this. Maybe Taoism has a hint of this in it. Western science just has to get back to that, you might say, figure background change in order to make sense of this stuff.
All right, well, let's wrap it up right there. This has been an intense and interesting and illuminating conversation. And so people want to learn more, read Terrence Deacon's book, Incomplete Nature, How Mind Emerged from Matter. Thank you very much. This has been great.
It's been my pleasure to talk with you.
Audio production and editing by Andrew Blevins Productions. Music by Tom Mull.